My name is Aaron Hutchinson, and I'll be presenting the paper Further Optimizations of CSIDE, a Systematic Approach to Efficient Permutations, Strategies, and Bound Vectors for ACNS 2020. This was joint work with Jason LeGrow, Brian Koziel, and Reza Azarderakhsh. So CSIDH stands for Commutative Supersingular Isogeny-based Diffie-Hellman. This is a key exchange protocol analogous to the classical Diffie-Hellman, except that we're using isogenies between supersingular elliptic curves. So this is a fairly new protocol proposed in 2018, and it's conjectured to be post-quantum secure. So here's a bit of the parameter setup. We're working with a prime p of the form 4 times L1 through Ln minus 1, where L1 through Ln are going to be distinct small odd prime numbers. N here is chosen based on the desired security level, and in practice we typically take L1 through Ln minus 1 to be the first n minus 1 odd primes, and we choose Ln as the next smallest odd prime, which makes p prime. So we'll be working with supersingular Montgomery curves. So for any a in Fp, we'll define the curve Ea, where a is the coefficient of x squared, and all the other coefficients are 1. We also define something called a bound vector, b, and this is just a tuple of n natural numbers that will define our key space. So a lot of what I'm going to say here is going to be an oversimplification of what's actually going on, so see the paper for full details. In practice, our private keys are going to be integer vectors, which we'll label as e, and each of these ei's will be chosen uniformly at random from the interval 0 to bi, where bi is from our bound vector. Given any one of these keys, as well as an elliptic curve, capital E, we can construct a new curve, which we'll label as E star E, as well as an isogeny going from the original curve to the new one, with the property that the degree of this isogeny is the product of the li's to the ei's. This construction defines a group action of Zn on the set of supersingular elliptic curves, which is why we use this star notation. In practice, unless the key E is very trivial, this isogeny phi won't really be feasible to construct at once. So what we do instead is construct phi as the composition of a whole bunch of small degree isogenies. So we'll construct ei many degree li isogenies. So let's take a look at the key exchange. We'll start with the Montgomery curve with coefficient 0 on the far left here. Alice and Bob will choose their private keys, EA and EB, and they'll apply the action of those private keys on the curve E0. So Alice will construct this curve at the top here, as well as the isogeny phi a, and Bob will do the analogous thing here on the bottom. And these curves in the middle will act as our public keys. So they'll each send the coefficient of these curves to the other party. And once Alice receives Bob's coefficient, she will apply the action of her key on that curve to get this curve on the bottom right here. Bob will do the analogous thing, and these two curves that we end up with here on the right will end up being isomorphic. And so the shared secret is just the J invariant of these two curves. So let's take a look at how one of these group actions is actually computed. So here I have kind of a toy example. I've set n equal to 6 here, so that we're only working with the primes L1 through L6. So we start here on the lower left with this point Q, and this is just some random point on an elliptic curve, such that the order of this point is some divisor of the product L1 through L6. To construct our first isogeny, what we'll do is multiply out all of the li's from this point Q, except for one of them. So here I've multiplied by L1 through L5, and this here now will be a point of order L6. We'll use this as the kernel generator for the first isogeny. So using this point, we'll construct phi 1 on the lower left here, and then we'll push the point Q through phi 1. And the act of doing that will remove the factor of L6 from the order of Q. We'll then try to construct the next isogeny. So now we need to multiply out, again, all of the primes except 1 from this point Q. So now I multiplied by L1 through L4 to get the point here in the second row on the right. And this will be used as the kernel generator for the next isogeny. So we construct phi 2, and we carry on in this way until we've constructed phi 1 through phi 6 here. Phi 6 is not actually shown here, but this point at the top is used to construct it. So after all of the operations in this picture have been carried out, what we'll have done is construct a single isogeny of degree Li for I going from 1 to 6. But remember, what we actually want is EI, many degree Li isogenies. So this will actually define one round of the algorithm, and we'll run a whole bunch of rounds using a diagram that looks either identical or similar to this one until we've constructed all of the isogenies that we need. So this is how the group action evaluation algorithm works as it was originally described, and our paper was about optimizing it. So we did that in a few different ways. We generalized the concept of strategy that was previously used in CSIDH and applied it to CSIDE. Within each strategy, we also found how to order the primes Li in a more efficient way. We determined how to choose a bound vector that increases performance without affecting security. And we also generalized the Simba technique that was previously introduced to allow for different strategies in each round, and also eliminate the primes Li once we are guaranteed that we won't need any more isogenies of degree Li. So taking all of this together, we determined new parameter sets for CSIDE and implemented everything in C. So let's take a look at each of these optimizations one by one. So what is a strategy, first of all? So here's the same picture that we looked at before. This is an example of a strategy. And basically, all we really wanted to do in this picture was construct all of the isogenies phi I on the left here. In order to construct these, what we need are the points on the upper right diagonal here, so the points on the leaf nodes. But there are many ways to reach these points. What we did here in this picture was kind of apply the isogeny first and then multiply. So we often refer to this as a multiplication-based strategy because most of the edges in this graph are multiplication edges by some Li. But there's other ways to reach these leaf nodes as well, such as this one. So, for example, to reach this leaf node on the second row, what we could do instead is just take this point, the fourth point that we computed on the bottom row, apply our isogeny to that one, and then we only need to apply a single multiplication to reach the second leaf. This also gives us a way of reaching the third leaf node by just a single additional isogeny evaluation. So these are two examples of what we call strategies. There are many that you could use, and our goal is to figure out what is the best strategy that we could use to minimize the runtime. In order to quantify what we mean by best, we'll assign weights to all of the edges in this strategy. So horizontal edges are always multiplication by some Li, and we'll denote the cost of that by f of Li. Vertical edges are always isogeny evaluations, and the cost of that only depends on the degree of the isogeny. So we'll label that as g as a function of its degree. Putting this all together, we call this a measure, and we write it this way. Oftentimes we'll leave off the f and the g because these only really depend on the type of curve you're using. So these will always be the same functions. We can then define the cost of a strategy as just the sum of all of the weights, and what we're looking for is a strategy with minimal cost. As it turns out, DeFeo, Zhao, and Plout already analyzed strategies in great detail for CSIDH. Theirs was a little different there because all of the primes that they used were equal to each other, whereas all of our LIs are distinct here. But they pretty much solved the problem entirely. They gave a recursive formula for the cost of an optimal strategy, and they were able to use dynamic programming to calculate both the cost and give a representation of the strategy itself. So in our work, we were able to generalize the approach that was used for strategies in CSIDH to strategies for CSIDE. So everything works out quite similarly with a few minor modifications. So we'll fix a measure, and the cost of an optimal strategy, which we'll denote as C of m for the measure m, is given through this recursive formula. The formula is recursive because for each strategy you can think of as kind of connecting together two smaller sub-strategies. So these two C of m's here are the cost of the two sub-strategies, and then these summations are just the cost of the connecting edges. So we take a minimum over the number of leaves in the left sub-strategy, and in this way we can get the cost. If you keep track of the index at which this minimum occurs as you go through the recursion, you can actually use those to construct the strategy itself. So this formula gives us both the cost and a construction for the strategy. I'll say a little bit more about strategies here. So one of the first optimization papers for CSIDE was by Meyer, Campos, and Reith, and they introduced a technique which they called SIMBA, which stands for splitting isogenies into multiple batches. So I'm kind of translating their approach into our framework, but the basic idea is to partition the measure m into a bunch of disjoint subsets, so they get measures m1 through mm, and for each I they just execute a multiplication-based strategy for the primes that are in mi. And what they found was, depending on the partitioning that they chose, this could end up giving a decrease in the runtime of the algorithm. So to build on top of their work, what we did was, for each of our partitioned measures mi, we'll use an optimal strategy si instead of the multiplication-based strategy. And furthermore, seeing as we know that our key values ei are chosen from this interval, we know that there will be at most bi many degree li isogenies. So what we can do is, as our rounds progress, we can actually remove the primes li from the measure once we know that we won't need any more degree li isogenies. So each round of our algorithm will actually consist of potentially a different measure, because we're eliminating these primes from the measure as we go. So in each round we will have a different measure, and we'll partition that measure into a bunch of submeasures, and then for each of those submeasures we pick an optimal strategy. So each round of the protocol we will pick what we call a SIMBA strategy, which is just this collection of strategy measure pairs that's specifically tailored for the primes that are left within that round. So the second optimization that we looked at involved permuting the primes li. So here I have the original picture that we looked at, and here what we're doing is constructing isogenies of degree li in the order of decreasing index. So first we did an isogeny of degree L6, and then L5, and then L4, and so on. But we don't have to do it that way. For example, here I've reversed the order of all of the li's, so that this point on the lower right here is now a point of order L1. And so the first isogeny that we construct would be degree L1 instead of L6. And then we do L2 and L3 and so on. The order that you use here doesn't matter, so you can permute these primes in any way you want, and permuting them affects the runtime of the algorithm. So what we want is a permutation of the li's, which results in optimal performance. So this was first observed by Meyer and Reith. So they noticed that you could just reverse the order from ascending primes to descending primes to get increased performance, but we can do better than that. So for a measure m and a permutation sigma, we'll define sigma m as the measure with where the li's are permuted according to sigma. So we'll fix the strategy S, and we'll compute the cost of the strategy S under the permuted measure sigma m using this expression here. So H and V here are two matrices that encode the horizontal and vertical edges of the strategy S respectively. So given this cost expression, what we're looking for is a permutation sigma that minimizes this cost for a fixed S and M. So to find the optimal sigma, our weapon of choice was linear programming. So we'll take this cost expression and turn it into something involving matrices. So we'll let capital sigma be the permutation matrix of sigma, and we'll define mu and iota as the cost column vectors that we get just from our measure. And that previous cost expression turns into this inner product here. So this is the Frobenius inner product. T here denotes transpose, and these J matrices are just an identity matrix with an extra column of zeros. The only thing that we require of sigma is that it's a permutation matrix, so these four constraints will guarantee that. And so what we get is an integer linear program here. Normally these are not easy to solve, but we were in luck here. If we just relax this last constraint and remove it, the resulting linear program with the first three constraints is actually guaranteed to have integer valued solutions. So what we do is just drop this one, solve the resulting linear program, and that actually just gives us the optimal sigma. The last optimization that we gave was about the bound vector. So recall that each of these private key values, EI, are chosen from some interval where these BIs make up the bound vector. What we're doing is constructing EI many degree Li isogenes. But if you just do that, then the runtime of the algorithm is heavily dependent upon the private key. So to fix that, what we do instead is construct exactly BI many degree Li isogenes, where EI many of them are real, and BI minus EI many of them are just kind of dummy constructions. So with that, our runtime depends only on the bound vector, the strategies that are used, and the permutations that we use. This isn't exactly true because throughout the algorithm you can have isogeny constructions that you just can't do due to some randomness involved. And so at the end of the algorithm you just have to kind of construct any isogenies that previously failed. So the runtime is not constant time, but it's pretty close. So we want to optimize this bound vector, but we have to be a little bit careful because changing the bound vector affects the security. So heuristically it's been shown that in order to ensure security, what we need is this inequality here. So the product of the BI's plus 1 has to be at least the square root of p. Optimizing the bound vector was kind of difficult because in order to optimize it, we kind of needed to know the values of S and sigma. But in order to find S and sigma, we kind of need to know the bound vector. So everything kind of depends on everything else here. So what we did was just fixed a single strategy and permutation to be used in every round. And this is not very realistic because we're going to optimize these on a per round basis later on. But there wasn't much that we could do here. So we fixed these. We derived a cost for the full group action evaluation using this S and sigma and a variable b, and accounting for these random failures that can occur when constructing isogenies. What we get is another program. So we're minimizing the cost of the action, accounting for the cost of these failures. And the constraints that we have here, this first one is just the security constraint, and these other two are just ensuring that we have a good bound vector. So what we get is an integer convex program, and we weren't so lucky in trying to solve this one because we can't just relax away this integrality constraint for free this time. So what we do instead is apply an iterative rounding technique to solve for the entries of b one at a time. So we relax this away, We solve the program. We round one of the entries of b to an integer value, fix that index of b, and then solve the program again. And in this way, we can get a b that's not necessarily optimal, but it worked pretty well for us in practice. So to summarize here, we want to optimize 3 variables, and if we fix any 2 of them, we have a way of finding a value for the third one that is either optimal or supposedly good. What we want to do now is start with a measure and produce a parameter set for CSIDE, so consisting of a strategy, a sigma, and a b. So the way that we do this is use algorithm 2 in our paper. And what this does is it takes a measure as an input, and it alternates between optimizing the sigma and optimizing the s using the approaches that I talked about previously. So it outputs a permutation and a Simba strategy S. So algorithm 2 here will just be one ingredient in our optimization pipeline. So what we want to do is start with our initial measure and produce a full parameter set. So what we'll do is run algorithm 2 to get an initial value for our strategy and permutation. And then we'll use those initial values to solve the program to find the bound vector b. Once we have b, the only other thing we need is the strategies and permutations to use in each round of the algorithm. So we'll look at our bound vector and we'll determine which primes, Li, will still be present in the kth round, and we'll form a measure out of it for that round. We'll then take that measure and put it into algorithm 2, and algorithm 2 will output a Simba strategy and a permutation to be used in that round. And in this way we get a full parameter set to use in CSIDE. So the last thing we did was to integrate our parameter sets into 2 previous implementations of CSIDE. So the first one was given by Meyer, Campos, and Reith, and using their code adapted to our parameter sets, we were able to get about a 13% speed up, so that was really nice. The other implementation was from Cervantes et al. And here we wanted to try to get a sense of which of our optimizations is actually impacting runtime the most. So number 1 here, the only thing that we changed from their parameter set was to optimize the Simba strategy and the permutation, but we use the same strategy and permutation in every round of the algorithm. So here this hardly impacted performance at all. We only saw a very minor speed up. Number 2 here, we chose an optimal Simba strategy and permutation for each round of the algorithm, and chose a minimal measure on each round. So this gave us about a 2.9% speed up, so we gained a little bit of performance there. And this last one, here we're using our optimized bound vector and optimized Simba strategies and permutations in each round of the algorithm. So this really applies all of our optimizations, and here we got about a 5% speed up over their implementation. So this was pretty nice. Thank you.